Good morning, NTT concept video. My name is Vishnu Vardhan from Electrical and Electronics Engineering, and my NTT tech concept topic is Laplace analysis of higher order electrical circuits with noisy sources. Among all increasingly difficult challenges, the target to low jitter to meet the timing budget is one of the main mission in optimizing multi-gigabyte I/O interface design. It is a common understanding that the dynamic range of supply noise needs to be confined because it directly affects the available voltage headroom for proper device operation and therefore causes circuit performance degradation or even leads to system malfunction. As the data rate gets fast, timing budget calculation is becoming a more important part of the equation. It is critical to minimize jitter effects and model jitter behavior more accurately and efficiently in order to help meet the aggressive high-speed interface target. The most important source of timing breakdown is power-induced jitter. The conventional method of simultaneously analyzing and simulating SerDes circuit in a highly integrated system on chip and a high count system consumes a lot of resources, and the problem of non-convergence may occur in a circuit simulator with a power transmission network S parameter model. This article proposes a method to meet the requirements of the chip package, substrate, and system power supply network. First step is to introduce duty cycle character circuit and clock buffer in SerDes circuit application in the section 2. Second step is to introduce supply induced jitter sensitivity mod modeling method in the time domain with Laplace transform method in section 3. Third step is to compare conventional simulations and the proposed methodology. Considering the scaled down power supply voltage and higher data rate speed, one of the most challenging tasks for system requirement is to maintain the integrity of the signal and power in the deep submicron technology. The general SerDes transmitter architecture is a serial to parallel converter and is sensitive to power supply noise. SerDes transmitters have several power domains which have different effects on the contribution of jitter sensitivity. The jitter sensitivity depends on the characteristics of each module silicon and is combined with the data and clock paths as shown in figure. Here we will focus on modeling the jitter sensitivity of the clock and data path caused by the power supply, including duty cycle collector and clock buffer, as well as pre-driver and current mode logic drivers. A duty cycle character with a feedback loop is usually used to adjust the duty cycle of a clock signal to achieve a high operating frequency with low jitter, high precision, and a wide correction range to improve the signal quality of the clock signal and ensure that 50% duty cycle ratio in high-speed signal. The function of duty cycle characters is shown in figure. The on-chip voltage regulator filters high frequency noise from the reference voltage and the forces the output to track the reference voltage as the core power supply. As shown in figure 4 and 6, sensitivity of the clock path is reduced by 2 to 3 orders of magnitude at 100 megahertz. The power supply rejection ratio is shown as 5. According to the sensitivity of the regulator, PSRR can be optimized to isolate the frequency where more noise appears on the PDN. The Laplace transform method provides an alternating method of correlating circuit behavior in the time and frequency domains, thereby facilitating simultaneous work in this domain. Laplace transient modeling is called by using Laplace in the source element sentence. The Laplace transform function is particularly useful in top-down system design. It uses a behavior transfer function instead of detailed circuit design. The Laplace transfer function can also be conveniently used in system design. The Laplace transform function can also be conveniently used in system level interconnect that contains nonlinear elements. Using Laplace transform can reduce the long simultaneous runtime of large complex analog physical layer. Frequency response is usually specified as two complex multiple patterns and real numbers. The frequency response can be expressed in the form of frequency table. Complex circuits are usually designed by interconnecting relative functional blocks with known frequency response. The proposed method uses Laplace transform frequency response data, which is used in general SPICE tools to convert the frequency domain response to the time domain response as a linear function block for simultaneous in SPICE. As conventional is x of t as a convolution of power supply, noise and impulse response ht, y of t equal to integral of x of t into h of t minus mu of d nu from infinity to infinity, where the h of t can be received from h of f as supply induced jitter sensitivity as figure 6 by the inverse Fourier integral as shown below shown. H of t is integral h of f into ej to pi f of f into t into d of f from infinity to infinity. This case is a Laplace transform function to represent the supply induced jitter sensitivity in the model as figure 7. Then we build the whole PDN connection including voltage regulator module, board package and on-die capacitance network. Then connect a supply noise source to the input of the model and to see its input and output. In this chapter, we validate the proposed power integrity analysis methodology through comparison with transistor level spice result. For passive comparison of the SI simulation accurates modules of active components, passive components, board packed on chip power model, and all need to be taken into account conventional. We had used SPICE simulator with transistor level circuit for the supply in used jitter in the past to check timing budget. However, this method generally took extreme amount of simultaneous runtime, with some cases taking up to even several days. In order to overcome this runtime, the proposed methodology uses an improved solution with Laplace transform model of supply in the jitter sensitivity in time domain. Case 1 uses sig- single tone sinusoidal noise with 100 mbp amplitude being injected into supply node as a stimulus. It shows the comparison between transistor level and Laplace transform model result as for power. The transistor level results as figure are 62.4 PS without on-chip regulator and 80.2 FS with on-chip regulator implement. Using the proposed method figure, the Laplace transform model results are 59.8 PS without on-chip regulator and 70.6 FX with on-chip regulator implement. A small difference of approximately is 4.1% as described in table. Case 3 uses passive components, board package on-chip current profile as figure, and on-die decoupling decoupling to generate on-chip supply noise as figure and is injected into supply node as a stimulus. It shows the comparison between transistor level result and Laplace model result at core power. The transistor level results in figure are 77.8 PS without on-chip regulator and 68 SS with on-chip regulator implement. The data path of SerDes transmitter have two supply domains which have great difference in the jitter sensitivity characterization. Here we will focus on supplying the jitter sensitivity characterization of data path including pre-driver logic and current mode logic driver as figure. The jitter sensitivity of data path is an figure. Case I shows the comparison between transistor level result and Laplace transform model results. 4 power the transistor level results are figure 17 or 28.9 PS using the proposed method figure. The Laplace transform model results are 27.6. A small difference of in table 1. Thank you.